We hear the term AI literally every single day, right? But we almost never talk about where it actually lives. So, welcome to this explainer. Today, we're going to unpack the fascinating, massive physical reality behind the artificial intelligence revolution. We're taking a full macro to micro tour of the modern AI factory, zeroing in on Supermicro's infrastructure designs. We're going to explore exactly how you build, power, and cool the massive brains behind tomorrow's technology. It's an absolute engineering marvel, and I am super excited to dive into this with you. When you picture artificial intelligence, you probably picture something abstract, right? Software, the cloud, invisible algorithms just kind of floating in the ether. But the physical reality of a greenfield AI campus is entirely different. It requires massive, modular, industrial structures just to house and power this tech. We're not just talking about code here. We are talking about concrete, metal, roaring generators, and heavy-duty infrastructure standing out there in the real world. So here's our game plan for today. We'll start with a basic AI factory blueprint, then look at their shocking 99-day deployment speed, the massive power and cooling required, risk management, and finally, we're going to zoom all the way down into the individual scalable server units themselves. All right, let's kick things off with Section 1. Welcome to the AI factory, understanding the blueprint. In these incredibly complex designs, every single critical system has a designated lane. Think of it kind of like a giant puzzle, organized by a factory color key. Red is entirely dedicated to processing. That's where the heavy lifting happens. Blue represents the massive cooling systems. Purple maps out all the management infrastructure. Green is your networking, tying the whole shebang together. And finally, beige represents the physical shell, the actual building itself. Keeping this color key in mind really helps you see that an AI factory isn't just a warehouse full of computers, it's a meticulously organized biological system. Moving right along to Section 2, deployment in under 99 days, the rule of 3. First up, we have this scenario called safe parking for liquid-cooled AI clusters. And the timeline here is just stunning. These highly optimized environments can be deployed in under 99 days in the US. No way, right? But it's true. And is made possible by relying on 4 core pillars. First, that blistering sub-99-day speed. Second, a highly specific microclimate featuring an hourly optimized liquid-cooled loop running at under 45 degrees Celsius. Third, incredible power flexibility. They can pull from the AC grid, DC microgrids, battery energy storage systems, and fuel cells. And fourth, standardized rack options accommodating everything from standard EIA sizes to open rack versions complete with rear door cooling and battery backups. Now, what happens when we move out to the edge? Well, when we look at liquid-cooled AI inferencing at greenfield edge sites, we see an exact match. It relies on the very same reliable 4-pillar foundation we just talked about. You get that same rapid deployment of under 99 days, you maintain the same microclimate-tuned liquid-cooled loops at under 45 degrees, and you utilize the exact same flexible AC, DC, and battery power options alongside the same rack configurations. The blueprint here is relentlessly consistent. And to round out our rule of 3, look what happens when we scale way up to massive, owned greenfield factories dedicated to AI learning. The framework doesn't change one bit. Whether you're building a safe parking cluster, an edge inferencing site, or a massive dedicated learning factory, you are using this exact same consistent rapid deployment framework. Under 99 days, precision liquid cooling, highly flexible power grids, and standardized racks. It is literally plug and play on a massive macroeconomic scale.
Okay. Section 3, massive power and cooling. We're talking literal acres of infrastructure here.
I really want this specific quote from the source material to sink in for a second. It says, AI factories have acres of cooling yard and acres of power yard enabling the power conversion and storage. Acres. We spend so much time obsessing over microscopic transistors and nanometer chips, but the physical reality requires literal acres of land just to cool those chips down and pump enough electricity into them to meet Supermicro and NVIDIA strict requirements. The scale is honestly just mind-boggling. So how does all that juice actually reach the racks? Well, it's a very precise journey. It starts at the standard AC grid, but these sensitive AI chips can't exactly just plug right into a wall outlet, right? The power routes through battery storage and fuel cells, transforming into clean, smoothed-out DC power within dedicated microgrids, before finally being distributed to the racks themselves. Basically, you have to iron out all the wrinkles in the electricity before it ever touches the processors. Next up, Section 4, Risk, Security, and Telemetry. Managing the operation. Running an AI campus requires some heavy-duty physical security and logistics. We're talking about secured campus perimeters equipped with massive 7-ton lift and store capabilities. You need to be able to move incredibly heavy, ultra-expensive equipment safely. They also utilize secured storage clusters that mostly just sit on standby, trickling in jobs as others finish up. And of course, because of the massive value and risk involved here, there are significant insurance and risk mitigations firmly in place. Now, managing all this requires some serious oversight, which basically splits into two distinct digital systems. On one side, you have comprehensive telemetry ledgers. Think of this as the data for the suits. It's for audits, insurance compliance, and keeping those warranties valid. But on the other side, you have microclimate live monitoring. This is for the engineers on the ground. It allows them to flexibly adjust to the environment on an hourly basis, ensuring absolute peak performance while aggressively cutting down on any wasteful power or cooling practices. And finally, Section 5. Inside the scalable unit, the hardware climax. All right, we've walked the perimeter, we've checked out the power yards. Now let's actually step inside that beige shell. This is what all those acres of cooling and power are feeding. These high-density, liquid-cooled server racks are an absolute masterclass in spatial engineering. They are cramming as much processing power into a single scalable unit as the laws of physics will safely allow. Just look at the specs on a setup like the NVIDIA Vera Rubin NVL72 configuration. Within this single scalable unit, you can pack in up to 32 GPUs. To handle the incredible heat that generates, it integrates up to 8 cooling distribution units, or CDUs. It supports up to 6 networking units to keep the massive amounts of data flowing seamlessly, all centered around those powerful Vera cores and Max-Q power delivery. It is a tightly packed, perfectly balanced matrix of processing, networking, and liquid cooling. Which kind of leaves us with one massive question, right? We've seen how these AI factories are rapidly deployed in under 99 days. We've seen the literal acres of infrastructure they demand and the unbelievable density of the scalable units operating inside them. So as this blueprint duplicates and scales from massive owned campuses all the way out to edge greenfield sites, how is the global power grid going to adapt to keep all this intelligence cooled and powered? It is undeniably the biggest physical challenge for our digital age, and the answer to that question will absolutely shape the future of our infrastructure. Thank you so much for joining me on this explainer, and remember to keep questioning what's behind the technology we use every single day.